feature inside of NeuroGuide called the time domain capture using the NeuroNavigator. Essentially, this allows one to explore in detail any single event or group of events that one may visually detect in the EEG, such as an epileptic spike or a gross pathology of some type, or whatever event you want to evaluate. It could be an alpha burst or a theta burst, etc. In this case, we are looking at an individual. Here is our demo patient who suffered a right parietal lobe injury. He's, as many times I've described, has spatial neglect and is paralyzed on the left side. And the way to activate this is you click View and then go down to and then select Time Domain Capture, which I've already done. Once you do that, then you slide depress your left mouse button and move the mouse over the events you want to evaluate or select, and then you right mouse click to activate to launch the NeuroNavigator. Now I've already launched the Navigator to save us a little bit of time. I'm going to bring it up here. And here we can see time point 488 is the time point I'm interested in. I can move my cursor around to whatever time you want to look at, or that's 489, 488. So I'm going to go over here to time point 488 and then evaluate time point 488. This is the Navigator. You can look at networks and symptoms, etc. For now, I'm going to do the full screen view, and you can navigate through just like you can with the other tools. But now we're looking at a single instant of time. It's the time domain, not the frequency domain. Now, one of the interesting features, if we go to volume view, is to evaluate the networks. Here we can go to connectivity, and I can select functional networks. And here we're getting all the networks. I'll remove the cortex so you can see it. And you can actually co-register these with the diffusion tensor imaging. I'm scaling it up a bit with the wheel of the mouse. And I'm going to go to networks and select a dorsal attention network. The sliders up here allow you to go up and down with the various slices to evaluate that network at that instant of time. You can also see the current density here in the brain, and you can see the value of the z-scores. These are raw z-scores going from 0.138 to 0.885 multiplied by 100, so it's scaled out, spread out a bit so we can see it. We can go through different networks. Here's the ventral attention network. You can see it's hypercoherent in the bilateral frontal regions, and it's hypocoherent over here, or much less coherent. The default mode network. Executive network, object and face recognition network, language network, that's left hemisphere, etc. So there's a wide number of networks here available to examine based upon the scientific literature determined by functional MRI and PET scans for the most part, mirror neuron network, salience network, tinnitus, schizophrenia. These are diffusion tensor imaging networks from the Catanian-Deschatten Atlas of diffusion tensor imaging. Now we're looking at the hubs. Now I'm going to click on the center voxel so you can see the center voxel here is the center voxel of the Brodmann areas that correspond to these different networks. I'm going to click on down so you can see more of the networks are available. There's Hagman hubs as well, and then more of the Catanian-Deschatten networks based on diffusion tensor imaging, Mosolum's data as a neurologist evaluating functional networks using PET scans and functional MRI, and then the interconnectivity networks published by Laird et al. Involving 30,000 PET scans and functional MRI. That's all summarized in the Handbook of Quantitative EEG and EEG Biofeedback, or if one wants, you can do a Google search and learn about all these things. Again, you can look at all of the networks, of course. We can also look at the diffusion tensor imaging of these networks. So you can see how they correspond with the tube. That is, we have two methods of evaluating connectivity. One is by looking at the center voxel of Brodmann areas and then calculating the coherence and functional connectivity between and effective connectivity between the center voxels of the networks of the brain. And we can also bring up the diffusion tensor imaging and color the fiber bundles depending upon their termination points on different parts of the brain. For example, the longitudinal fasciculus in the left hemisphere would be frontal occipital longitudinal fasciculus. So you would see the voxels that represent the frontal part of the frontal occipital fasciculus and the coherence between those voxels and the voxels in the occipital lobes, representing where the termination point is of the frontal occipital fasciculus. And that's true of all of the various diffusion tensor imaging networks. Again, we can take a look at here's the anxiety network. It's a good idea for now to remove the diffusion tensor imaging, so you can see these networks with respect to the Brodmann areas, which is the typical way that functional MRI PET scans look at them in terms of the connectivity. And the data type allows us to evaluate different kinds of connectivity. That's lag coherence. And there's just phase differences. I don't believe we have phase slope index yet, which is effective connectivity, measuring the magnitude and direction of information flow using the phase slope index. But in any case, this gives you an overview of the time domain capture tool that supplements the old Key Institute time domain capture tool that was limited to the current densities only and did not provide networks. And instead, what we have here is the ability to evaluate these same things, but with 12,700 voxels using the boundary element method for the inverse solution. There's as opposed to the spherical head model that the Key Institute used. That improves the localization accuracy. And I'm going to go ahead and look at some others. That the SW Loretta, or the standardized weighted Loretta, can achieve, that we're using now, compared to the older Key Institute Loretta, which is excellent. It's just that it was an average brain. This is using the actual MRI from the Collins database of a single MRI. It's a template that's a standardized template used now throughout the world, because the resolution of the inverse solution doesn't make any difference if you have individuals MRI or diffusion tensor imaging, or use the template, because the amount of anatomical variation is greater than the localization of the accuracy of localization using low resolution electromagnetic tomography. So it's really useful to have the template, standardized template MRI, to co-register the sources and network hubs for any given event that you want to evaluate here in the EEG. So there may be some other events you want to see. We could go over here and look at time point 142. I'll have to go up to full screen. And now we can look at that event. So this is a heads up on this new time domain capture. And it'll be in the next release of NeuroGuide. So thank you for watching.